A central challenge in physics is explaining how the stable, predictable reality we experience emerges from a state of disorganized chaos. To study this, researchers look at a digital environment called the Stage 2 cloth, which is built from cross-linked bundles of quantum events. At small scales, time exists only as a background coordinate, an external reference for updates that doesn't rely on the events themselves to function. Because of this, the individual events have no internal synchronization or a shared ticking clock. Without a map showing when this probabilistic soup solidifies into a stable structure, it is impossible to use these simulations to model larger systems. Researchers navigate this system using two primary dials. There is system size, which is the total count of events, and coherence, which represents the strictness of the rules governing how those events connect. The goal is to sweep across these variables to find the mathematical boundary where random events lock together into a cohesive whole. This is a cartographic mission to draw the first empirical map of how space and time emerge within the cloth. The investigation begins by isolating a single slice of data, setting the coherence dial to 0.8 to look for structural changes. As the system size increases, the simulation remains stable until it hits a specific threshold. Between sizes 23 and 24, the structure undergo a sharp, sudden shift. This drop represents the knee. Researchers measure this using the core fraction, the ratio of events in the center of the cloth versus the total count. At the knee, the system flips from a clumped core dominant state to a stable halo dominant one. This shows that spatial stability doesn't build up slowly, it snaps into place once the system reaches a specific size. Space is only part of the map. To see if the system has synchronized, researchers look at clock quality, a metric that tracks how well the internal events have aligned their timing. Near that spatial knee, the simulation enters a metastable band. If you run the simulation multiple times with the same settings, you get different results. Some runs fail to sync their clocks, while others lock into a stable rhythm. But as the system size dial is turned up past the knee, the probability of a failed clock reality shrinks until only the stable, locked mode remains. In this regime, the emergence of a ticking clock is a matter of probability, a game the simulation eventually wins as it gets larger. One landmark helps, but to understand the physics of the entire system, researchers must sweep all parameters to see how they interact. This 2D grid allows us to compare system size against coherence. By plotting the knee contour, we see the boundary where spatial connectivity changes. As coherence increases, the system needs a much larger size to reach that spatial flip. Then we add the lock contour. This is the operational boundary where the chance of a clock failure drops below 5%. Together, these lines allow physicists to separate the exact moment the cloth connects spatially from the moment its clock synchronizes. Researchers no longer have to rely on trial and error to find stable configurations in the Stage 2 cloth. These phase boundaries are now documented and predictable. The data shows that stable structures depend on a specific interplay between the size of the system and the strictness of its coherence rules. This map provides the necessary coordinates for the next stage of research, the Stage 3 supergraph tests. Using these contours, researchers can now purposefully target the chaotic near-knee region for sensitivity tests, or the stable post-knee region for geometric analysis. By establishing this foundational map, physicists have the necessary coordinates to test how complex structures form in the next stage of the simulation.